Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 20th, 2026, just 2 days ago. It introduces a unified framework that successfully handles identity, style, and motion transfer all at once, matching the performance of specialized pose-based models while cutting generation time by 20%. The paper is titled OmniTransfer All-in-One Framework for Spatio-Temporal Video Transfer. And as we'll see later, the way it decouples reference and target branches offers some really promising implications for high-fidelity video synthesis. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 demonstrates OmniTransfer's core promise, a unified framework for diverse video tasks. On the top left, the spatial appearance section handles identity and style transfer, for instance, preserving a specific face in a new piano playing scene. Moving to the top right, temporal transfer captures dynamics like complex dance moves or underwater effects. Finally, the bottom rows highlight the model's flexibility by combining these tasks, merging a specific identity with a distinct artistic style or dramatic lighting effect. While Figure 1 showcased the results, Figure 2 unpacks the architecture behind them. On the top left, the reference latent construction encodes the input videos into a compressed format. The top right shows the task-adaptive multimodal alignment, which uses a multimodal large language model to create task-specific guidance. This feeds into the reference-decoupled causal learning module on the bottom right, where the model generates the target video while keeping the reference stream stable. Finally, the bottom left details the task-aware positional bias, which adjusts the spatial and temporal embeddings to align features correctly for the chosen task. So, having seen the architecture, Table 1 explicitly lists the specific video tasks OmniTransfer is built to handle. The top section covers appearance transfer, which focuses on preserving identity or style using a text prompt and a reference video. The bottom section details temporal transfer, encompassing motion, camera movement, and visual effects. Here, the setup changes to an image-to-video format, where a reference video and a single starting image guide the generated output's dynamics. Moving to the results. Figure 5 demonstrates the framework's performance on the temporal transfer tasks we just discussed. The top section visualizes effect transfer, where the model successfully applies dynamic elements, like the burning heart effect seen here, onto a new subject, outperforming baselines like WAN 2.1. The middle panel focuses on camera movement transfer, showing how the system replicates complex trajectories, such as tracking shots, with greater stability than competing methods. Finally, the bottom section highlights motion transfer, where the model accurately drives a target character to mimic reference dance moves, matching the fluidity of pose-guided approaches without requiring explicit skeletal data. To understand precisely what drives these improvements, Figure 6 presents a qualitative ablation study. The columns illustrate the incremental benefits of adding each module, first the baseline, then the task-aware positional bias, followed by the causal learning, and finally the multimodal alignment. In the ID transfer examples at the bottom left, notice how the subject's identity becomes significantly clearer and more faithful to the reference as we move to the rightmost column. Similarly, in the pose transfer section on the far right, the baseline creates visible artifacts or blurring around the face, while the fully equipped model produces a sharp, coherent image. So, while Figure 6 gave us the visuals, Table 7 provides the hard numbers for those same ablation steps. The first row establishes the baseline performance for consistency and quality. As we move down and add the positional bias and causal learning components, you can see these scores consistently rise. A standout detail is in the time column on the far right. Adding the causal learning module cuts the generation time from 180 seconds to 142 seconds. Finally, the bottom row shows that the complete framework achieves the best results across the board. Wrapping up, 2 key takeaways stand out. First, OmniTransfer successfully unifies identity, style, and motion tasks without needing explicit pose priors. Second, its decoupled design not only improves fidelity but also cuts generation time by 20%. This suggests a shift toward more versatile, efficient video generation tools. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.